Hello, everybody. My name is Dana, and I'm here with my colleague Martijn, and today we will discuss about USB-based attacks. At Rescure, we do a lot of embedded research, and today we would like to tell you the story of how we used what we call the forgotten vulnerability to compromise our target by just inserting a malicious USB device. So our agenda for today is the following. We will discuss about the relevance of USB-based attacks. We will then tell you a little bit more about the forgotten vulnerability. After that, we will share our exploitation methods and approach, and we will show you how this attack looks like by giving a demo. And we will conclude our presentation by giving a few discussion points and our final takeaways. So why do we care about USB-based attacks? So there are several reasons for this, but here we will only mention the ones that we consider that are the main ones. The first reason is that the USB interface is available in pretty much all devices. Even closed-down devices actually support typically USB interfaces. The second reason is that the USB interface is generally available from the moment the device is powered on till the moment the device is powered off. That makes it really interesting. The third reason is that the USB protocol is quite complex, and that makes it error-prone. Cscholar has demonstrated in the last few years that there are still a lot of vulnerabilities to be uncovered in the USB drivers of the Linux kernel. And these vulnerabilities get found, but they also get exploited in the wild, and recent research has shown the potential of such vulnerabilities. So now we can move forward to the forgotten vulnerability. So what is this vulnerability about? This is basically a double free in the Linux kernel. While we were doing research on our device, we found this vulnerability to shortly after discover that a researcher called Andrey Konovalov also found it in 2016. He actually made a really nice blog post where he explains about the vulnerability and his exploitation approach. To give a little bit more details, this is a vulnerability in the USB midi subsystem. Andrey demonstrated that it was possible to both cause a denial of service in the Linux kernel, but also gain code execution. So he managed to turn this double free vulnerability into a use after free, and he used these two primitives to actually shape the heap and bring it into an exploitable state. These are the syscall interface, and also he used sockets in order to do this. So now you may be asking yourself, USB MIDI devices are not that common. Why do we care about this vulnerability? Well, the fact is that this driver was enabled in pretty much every device that uses Linux. This meant that the issue affected even major distributions such as Ubuntu and Fedora. Of course, in order to exploit this vulnerability, you need physical access to the device. So now you might also be asking yourself, why do we still care, right? This vulnerability was found 5 years ago. So we wanted to share a little timeline with events to answer that question. So in 2016, Andrey found the vulnerability, and shortly after, the issue was patched upstream and a CVE was assigned to it. 4 years later, when Martijn and I were doing research on a device, we stumbled across this vulnerability, and 2 months later, we actually had a successful exploit running. This is the story that we will tell in this presentation, how we managed to do that. So just to give you a little bit of background on the device, this is a broadly used device that's probably in millions of households. It had a pretty trimmed down version of Linux that was based on kernel 4.x. And as far as we could see, they were actively backporting all the security fixes, or at least most of them. The most important characteristic of this device is that it was completely locked down. So our attack surface was really limited. We only had one USB interface, then a network interface, and a heavily sandboxed browser. On top of that, we did not have any sort of output. So upon crashes, we could not see anything. The actual device is not relevant for this talk. What we want to show is our exploitation approach and our methods. So now let's dive a little bit deeper into the vulnerability to see how is this triggered. So triggering this vulnerability is surprisingly easy. You just need to connect a misconfigured USB MIDI device and you will cause this to happen. So when you insert a device, a process called probing will start. So the Linux kernel will start the process to find the proper drivers that can handle that device. And an important thing to know is that the probing process is driven by the host. In this case, the host is our target. So it all starts with the USB hub work queue. And this work queue basically contains all the events that the kernel needs to handle related to USB. Then after that, a handshake will start between the host and the device we insert. And the host will be asking some questions like, who are you? What are your capabilities? What's your name? And there can be more messages depending on the first exchange. The important thing to note there is that the device that we insert does not have a lot of freedom. It just needs to reply to the host requests and reply in a specific format. So along the road, then we will start initializing objects, and we will end up in the code that handles MIDI devices. Then the kernel will decide to allocate an object, which here we call umidi, on the heap. Since we are inserting a device that's misconfigured, the kernel will also realize that this device is not properly showing its information, and this will cause the first free of this object that was allocated. But the process doesn't stop there, because the error will be propagated, and then as a probing failure result and as the aftermath, there will be a second free. This is basically what causes the vulnerability to happen. So let's now talk a bit about the Linux memory allocator. So since a really early version of Linux, slab is the default allocator. This is the subsystem that handles allocations and the allocations of the kernel. And the important thing for us is that in order to handle memory, this allocator groups chunks into structures that we call slabs. So basically, all the objects that are of the same size end up in the same slab. The thing is that, of course, not all the objects are going to be of the same size. So upon receiving certain allocation requests, the kernel will check it, will round the size to an appropriate slab, and then the slab will be chosen. The slab allocator also needs, of course, a way of keeping track of the chunks that are available for giving when a request comes. This is done by using a free list. That's basically a single linked list. Another important thing to know is that this single linked list is handled in a sort of a FIFO way. So first in, first out. That means that the first object that is inserted in the list will also be the first object to be given upon a memory allocation request. And this specific behavior is really important for shaping our free list. So in order to see what happens with the heap while this vulnerability happens, we will see a series of images. First, we start with the free list as the kernel has it before anything happens. Once we allocate the umidi object, the free list shape will change. We will give away chunk 1, so then now the free list will be pointing to chunk 2. When we do the first free, if no other allocation happens in between, we will get back to our initial state. We will have the free list with all the chunks because chunk 1 will return. The problem is that when we do the second free, again, if no other object was allocated in between, we will end up in this situation. This basically means that with this vulnerability, we managed to corrupt the free list of the kernel. And from this point on, the kernel will constantly give this same chunk to all the allocations that are requested. This opens the door for memory corruption attacks. And as a closing remark for this section, we want to show you the fix. So basically, the fix consisted in just removing one line of one of the frees, and that was it. Then the vulnerability was fixed. Now I would like to give the floor to Martijn, who will talk about our exploitation approach.
So let's talk about how we exploited this vulnerability and the approach we took to develop our method. So as we have seen, devices are severely constrained in what they can do when they are communicated with the host. And in principle, they only can respond to the request the host is sending to the devices. That means that devices cannot initiate arbitrary communication or send arbitrary data back to the host. And this is severely limiting the exploitation primitives we have to our availability. To understand what we are working with, we need to take a deeper look at the midi object and how what is happening with the heap of the system. So the midi object is a structure of 272 bytes of memory, and it gets allocated on the kernel heap. And because it is 272 bytes and the kernel or the slab allocator is rounding up its sizes, it means it will land on the slab for 512 byte objects. And this slab has interesting characteristics, at least interesting characteristics for exploiting the system. What we found is that 512 bytes is a nice amount for crafting our attack, but what's way more important is that this slab is a relatively low activity. Actually, we have noticed that this slab seems to be mostly used for network-related activity, and that are then also the things that might be interfering with our attack. Due to the fact that this is a relatively low activity slab, this has been really one of the key characteristics that allows us to exploit this vulnerability on the system, because we have to win the race between the double free and the actual fact that something is happening with the heap again. So how are we going to turn this double free into something that is actually useful? Because after the double free, we have a loop in our free list. What we noticed is that all allocations that occur on the same CPU core and on the same slab actually are getting the same memory chunk assigned every time you do an allocation, as has been explained by Dana. However, this is just panicking the kernel in a matter of seconds. So what is happening? Well, we do multiple allocations. Each of them are returning the same address due to the loop we have in our system. Because it's a linked list, what we actually have is we have the start of the list, but we also have a pointer to the next chunk. This pointer is stored at the first 8 bytes of our chunk, and due to the loop in the list, it is pointing to itself. That also means that when we are updating the free list or actually allocating memory, we will take this pointer from the start of the chunk. Which means that when we have an allocated chunk and we are writing data to it, due to the loop in the free list, the next allocation will actually start using the address that we had at the beginning of that chunk. Which means that if we have 2 consecutive allocations and we control the content of those allocations, we can actually make the free list point to an arbitrary location in memory, and the third allocation will then return the address we have put in the free list pointer. If you then control the content that is written to that address, we have an arbitrary write primitive in our system. And this is the base primitive for our exploit. So what do we have? We have a chunk on the 512 byte slab. We need to have 3 memory allocations in a row, and we need to control the data of those memory allocations. Ideally, we control the content that is written to all allocations. However, we can get away with if it's only controlling the first and the last allocation. The first allocation, we need to set the address that we are going to target with our write. And the third allocation, what is written to that allocation is actually the payload that is being delivered to our arbitrary memory location. However, where are we going to write an exploitation primitive with exactly these characteristics that is also accessible over USB? And we have been digging through several USB drivers. And at a certain moment, we were encountering a very interesting USB driver. And this USB driver is the USB HID protocol, or human interface devices. And it is basically a generic protocol for keyboards, mouses, game controllers, etc. And it basically allows you to describe your device through a series of inputs and outputs. And the way it works is that the USB protocol is extended with 2 additional descriptors. The first one is the HID descriptor, and the second one is the HID report descriptor. And the HID report descriptor is basically an arbitrarily sized blob of data that is describing your device. And the interesting bit of this is that this report descriptor has a variable length, gets dynamically allocated, and the actual length that will be allocated is delivered in the initial HID descriptor. So let's now take a look at the probing process that happens for HID devices. One of the main functions that is doing the probing is the USB HID parse function. The USB HID parse function will first request the HID descriptor, and the HID descriptor will have the size of the report descriptor, which is then stored in the rsize variable. Then it will start allocating memory for storing the report descriptor and actually call the corresponding function to retrieve the report descriptor from the device. This is done by the HID get class descriptor function. But then as a next step, we start actually processing this report descriptor. And there we see some very interesting behavior. This happens in the HID open report function, which is quite a bit later in the probing process of this device. And interestingly enough, this driver is making 2 copies of our report descriptor buffer. And it's just allocating the same size of memory and just copying over the content of the buffer. The kmem_dump function is basically a combination of a kmalloc and a memcopy with the purpose to duplicate a buffer. However, what we have here are our 3 allocations in a row and the content we control. AKA, we have here our arbitrary write primitive that we can reach from outside over USB. But how are we then going to exploit that on the real device? Because remember, on the real device, we have no way to see what is happening in the device. The device might work, the device might crash, but that's all the information we can get. We have no insight in what's happening on the device. And due to that, we invested heavily in creating a development environment that allows us to actually develop the attack before we try to execute it on the real device. And one of the main problems we have is how do we craft our attack in such a way that we reliably win the race between the double free and actually allocating the buffer for the report descriptors, but also how are we crafting a payload that is working for our specific target. Luckily enough, we did have access to the plain text binaries, which helped us a lot. However, we have no information from the runtime of the device. And what we did is we actually did a lot of work in preparing our attack using the QEMU emulator. What we did is that we basically tried to model the real device as close as possible in the emulator. And this has as major benefit that we could completely control and debug our attack before we had to do it on the real device in the blind. And this has been really critically to get a sufficient understanding of how the attack is behaving and the elements that we need to control to make it work. Of course, an emulator is not a real device. The binary is different, the device behavior is different, the activity is different. However, we really tried hard in making sure that all the critical code paths and all the data structures are as close as possible to the real device, also by comparing our emulated kernel with the real device kernel. However, until the very last, it remained the question, how accurate is the emulation that we are doing on our device, and how is it actually mapping to the real environment? So in QEMU, we can, of course, test our kernel, but how are we going to test the real attack? And what we did is we actually took the emulated devices of QEMU for USB, and we basically repurposed them. So we took the mouse and we made a MIDI device out of it, which has the invalid configuration triggering the double free, and we changed the tablet interface such that it is using its HID report descriptor to deliver the payload, which then gets copied and written to memory to the address we want. And to our real surprise is that we almost had to change nothing, only, of course, the addresses and the offsets and similar things, but it almost worked out of the box on the real device. And that was really a surprise to us. But how are we actually going to do this on a real device? Because you will not find a USB device that first represents itself as a MIDI device, doing a double free, and then say, hey, I'm an HID device, and I want to deliver a payload that it gets written somewhere in your address space. And what we used is the Phase Dancer framework, which is a very nice open source framework to implement arbitrary USB devices in Python. And we then used the Great Fat Board to make it interface with our target. And what we did is we changed the Phase Dancer framework in such a way that it first connects a MIDI device, triggers a double free, disconnects itself, connects as an HID device, and delivers the payload. And hopefully that results in something useful for us. What's very critical here is that the triggering of the double free, the disconnecting, connecting, and delivering of the payload need to be as close as possible. The timing of the allocation of the report descriptor should be as close as possible as the triggering of the double free, because if there is something else trying to use this slab for a different purpose, that might crash the kernel due to the corruption we have caused. But what is the kind of payload we are actually going to deliver? And one of the main questions there is the code of the kernel writable. If the code is not writable, you will have to resort to some form of a data-only attack. However, in our case, we could actually override the kernel code because it was mapped writable on this very specific device. And by overwriting the kernel code, we could get arbitrary code execution in the context of the kernel. But one of the main questions here is, where are we going to hijack the kernel code and get code execution and do something for it? Naturally, for us, one of the logical locations to take control would be as close as possible where our payload is written to memory. This is the assembly code of the HID open report function, and we see the two QEMU calls inside the code. We want to target our payload to start executing as close as possible after the second QEMU, because this is the function that is going to write our payload to memory. What we did is actually we overwrite the code slightly before the branch to this function, because due to the start of our payload having the destination address that we want to write to, which is not executable code. And then when the QEMU returns, it will actually start executing the first instruction of our payload. How are we then designing our payload? Well, what we did is we again went back to QEMU and we started crafting different payloads. And our very first payload was simply calling the print function and seeing we could print a message to the console and seeing how the kernel panicked. Of course, this is not very useful. However, it gave us the confirmation that we could actually gain code execution in the context of the kernel. The next step that we did, and that was also very useful to do on the real device, is calling the USB get string function. This is going to do a get string descriptor request to the USB device, and this is one of the very few things we could observe from the outside. What would happen is when we take control of the kernel, is that when we call this function, we see on the USB device that the kernel asks for a string descriptor that we specify. While this is very likely that the kernel panics afterwards, at least what we can see is that we successfully got code execution on the device. And then we went through several iterations, and the final version of our attack, we could actually clean up the mess we have caused inside the memory of the device, such that we could run the exploit pretty much an indefinite amount of times on this specific device. So how does our payload look like? Well, as I told before, we are constrained in size to 512 bytes. And at the very start, we have the destination address where we want to write our payload to. Then we have some mandatory cleanup steps to prevent the kernel from instantly panicking the moment we deliver the payload. And then we have the actual useful part of our payload. This could, for example, be running a shell command as root, extracting some data like cryptographic keys, or disabling some of the protections like SI Linux. To be able to actually run the attack multiple times, we need to augment our payload with some other steps. For example, we need to restore the code, or at least the most critical parts of the code we have overwritten. We need to clean up, and we need to do a proper return and make sure the probing process fails, because that way we can actually trigger the probing multiple times and get code execution multiple times. And we can simply make the actual useful part of the payload differ each time we get code execution. And for example, run different shell commands each time we execute our attack. So what are we then going to execute, for example, on the device? Well, we can run arbitrary commands as root using a function in the kernel called run command. This is a well-known technique to turn an arbitrary code execution in the Linux kernel in actually doing something useful. However, something we noticed is that this function does not function from the interrupt context, which is exactly the context the USB hub work queue work under. So when we actually tried using this function, our kernel would panic because it is not valid to be used that way. Alternatively, you can use the system work queue to schedule the start of a new process by pushing this as a work item onto the work queue. And then the system work queue will take care of it, that the process gets started. Luckily for us, there is already a mechanism in the kernel that does this and that we could simply repurpose. There are the functions orderly reboot and orderly shutdown that basically are scheduling the execution of a command through the system work queue and then calls the run command function with this command. And these commands that get executed are writable with our specific kernel. So we could simply change the command and call the relevant function. So what are we then going to execute with root privileges? Well, we can of course pick any binary we want in the file system, but as we told before, this is a very minimal system and there are effectively no useful binaries in the system. However, we are doing a USB attack, so why not use a USB stick? And that is indeed what we did. We simply were putting a reverse shell binary on a USB stick, which we then were running from using our exploit. Of course, ideally, the USB stick gets auto-mounted by the system. In our case, we had to do a little bit more work to manually mount the USB stick on our device. And what about SL Linux that might prevent you to spawn new processes? Well, we simply had to disable it. For example, in our case, we could set the enforcing variable to 0, which is a well-known technique, but you could, of course, also patch the in-memory policy database or use one of the other techniques that are known. So we have prepared a demo that is demonstrating our attack. We have recorded our demo for the presentation, which we now would like to show to you.
In this demo, we would like to demonstrate the attack we have discussed so far. We took a several years old smartphone which has a Linux kernel that is quite similar to the device we originally exploited using this vulnerability. Updated to the latest firmware version, the phone is not vulnerable to this attack. Therefore, we created and installed a custom kernel that contains the vulnerability as well as a few small modifications, such as disabling some vendor-specific kerneling hardening the original device didn't have. On the right side, we have a netcat instance waiting for incoming connections. When we gain code execution in the context of the Linux kernel, we will use this to launch a reverse shell on the phone that connects to the netcat instance, giving us a shell on the phone with root privileges, which then allows accessing the phone's data. On the left side, we are going to run the exploit implemented in Python using the face dancer framework. First, it will connect a MIDI device that triggers the use after free vulnerability. Then, it disconnects and connects the HID device, delivering the payload with the shellcode. All of this will happen within a few hundred milliseconds, and you will see the USB communication quickly scrolling by. The longer these two steps take, the lower the probability we win the race. However, we notice that when the device has been idle for several minutes, we have a quite high chance of success. As you can see on the right side, the attack worked and we have an incoming connection, showing we successfully got a root shell on the phone, giving us full control over the Android environment. As this is a demo, we will use this to show how this allows unlocking the device by simulating physical input. However, if the phone is already fully booted and unlocked before, exploitation of this vulnerability gives immediate access to all data stored on the device.
And now we will talk about our discussion points. We will first want to discuss about the attack challenges. As Martijn mentioned earlier, winning the race is one of our main challenges. We need a very specific sequence of events to succeed. And this is basically inserting the USB MIDI device to cause the double free, disconnecting it, connect the other device to deliver the payload. So if we are dealing with slabs with low activity, we will have a high chance of winning the race. Whereas if we would be dealing with high activity slabs, that would be more complicated. So that's something to take into account. The second thing is the cache behavior. Since we chose to override the kernel's code, caches could make it hard to predict where exactly we are taking control. This could be mitigated, of course, by adding an ops sled, but you need to have space to fit it in your payload slot. And the third thing we wanted to discuss is about exploit mitigation. So what if the kernel has address space layout randomization? This is a hurdle that we will need to overcome. So either finding another vulnerability to leak a pointer or an address of the kernel so we can then dynamically calculate our addresses, or we could also choose to brute force it. But this approach has the downside that, of course, the kernel will crash if we don't hit the correct address. And in some cases, this might not be acceptable. The second thing are all kinds of protections. Code and data can be protected. So then if that happens, we need to look for other attack paths, either a data-only attack, or also we can think of, for example, trying to override privileged process code from the kernel's fizz map, which would allow us to gain control as well. And the third point is all kinds of heap hardening techniques. So for example, the free list metadata could be checked, or the allocations could be randomized. Those are all factors that could make our attack impossible to execute. If we talk about applicability, we think that similar bugs in a low activity slab could be exploited using our methods. But of course, the precise steps of the exploitation will really depend on the device. There are different factors to consider, such as the architecture, the device configuration, vendor-specific customizations, and the exploit mitigations. About our exploit requirements, as Andrey's exploit, we of course need to have physical access to the device, and we need this vulnerable driver to be enabled. With our approach, we managed to remove two of the prerequisites because we don't need to have unprivileged code execution, since we are doing everything from the USB subsystem that runs in the interrupt context of the kernel. And we also don't need any other interface. We are just using the elements we have with the USB protocol stack. But as we mentioned several times already, we do need a low activity slab, because for us, it's not that easy to keep bashing the heap until we win the race. So this is a prerequisite that's quite important. And now we would like to conclude our talk with three main takeaways. The first takeaway is that even though vulnerabilities might be easy to fix, as we showed, it's not that easy to propagate all these fixes to devices that are already deployed on the field. Another thing we learned is that investing time in your debugging environment is very important. So this really allowed us to see to the detail what was going on with our exploit. And actually, it was quite easy to port it to the actual device once we have done all the work of replicating the environment. And the last thing is that USB attacks are quite powerful. And in this presentation, we demonstrated how we could compromise a device by just using the USB protocol. Sometimes it might even be your only attack vector. And with this, we would like to conclude the presentation and ask whether there are any questions.